Thanks, everybody. Hi. My name is Chris Dickinson. I work at Urban Airship in sunny Portland, Oregon. It's not that sunny, but we'll blur our eyes. I'd like to talk to you today about how we interact with our code. And to start, I'd like to show you some JavaScript. This is how we usually see our code. But there's treachery afoot. This isn't really JavaScript. It's text. More than that, it's text that's represented as a series of bytes on a hard drive. And that's how we usually interact with our code. We search it by entering text and finding lines of other text that match that text. Sometimes, if we're feeling particularly tricky, we'll pull out a regex and set that happily nom on our bytes and tell us where things are, or change text from one form to another. But this is not just text. It's a series of tokens. It's a series of tokens assembled into a tree. It's a tree that represents instructions. It's a set of instructions that elicit actions from a virtual machine. It's a potential series of actions that cause electrons to hurtle from one side of a motherboard to another to manipulate a register. This text represents many things. Each of these views on this code are true. Each view is a different facet of what this text represents, a different level of abstraction. What we do when we type text and search text and replace text is a bit like changing the shape of a shadow to change the shape of a sculpture. Each level of abstraction carries information that the others don't, or each of them is better at expressing certain things than others. Today, I'd like to talk to you about working with your code on a different layer of abstraction at the AST level. So, time for first demo. Let's see how this goes. Okay. And, okay, demo 1. We'll just do npm start. And everything will be okay. Maybe. Okay. Perfect. Sweet. So the first thing that happens is tokenization. Sorry, I am missing some stuff. Or AST stands for abstract syntax tree. It's the second derivation from our text, the first derivation being tokens. To get an AST, we first run lexical analysis over our input text to get these tokens. And then we consume these texts with a parser to create a directed tree of nodes. So, okay. Tokens represent types of words, just like most languages have nouns, verbs, and adverbs. Common token types are identifiers, keywords, and operators. So, operators being things like the not equals equals, keywords being things like type of, identifiers being things like request animation frame or window. The purpose of tokenization is to move from a level of abstraction where the world is all bytes, the text that we see, to one where groups of bytes exist with more semantic meaning. We then parse our tokens into a tree of nodes. There are many different approaches to this. If you're curious about how to build a machine that does this, I would highly recommend Douglas Crockford's article on TDOP, which stands for Top-Down Operator Precedence Parsing. It'll show you how to tokenize and parse a language that's very close to JavaScript, the good parts, using JavaScript, all of the parts. In this demonstration, we're watching as tokens get consumed by the parser to create an AST. Note how we move from the innermost, deepest nodes to the outermost and shallowest. This is called a depth-first traversal. Each node has a type, what structure it represents in the language. Most nodes have a parent node with whom they share a labeled relationship. For example, if statements, which it's a little blacked out, but you can kind of see it, hopefully, have a child node called test. This represents the code between the parentheses of your if statement. So in that if statement on the second line there, the test is the node that represents the outermost of not ops.stats disabled. This code is borrowed from Voxel Hello World. So thanks, Max Ogden, if you see this ever. So they also have a child called a consequent, which is the block that represents what happens if the if statement is true, and an alternate, which represents the other case, the else statement. So some nodes, like the aforementioned if node, are statements with no return value, but they represent special meaning, switching based on the test, the evaluation of the test node. Others are expressions which do return a value. So the inside of the test node has to be an expression because it has to return a truthy or a falsy value. At this level of abstraction, we lose comments, but gain an ability to talk about the overall structure of our code. Furthermore, the actual text contained within the identifiers, the user-specified variables, members, etc., no longer matter quite so much. Two textually different programs can produce identically shaped ASTs. Minification is a great example of this. So that is demo 1. And now back to Keynote. In JavaScript, for JavaScript, you don't necessarily need to worry about writing your own parser. There are many implementations of JavaScript parsers in JavaScript. This is one of the benefits of having such a relatively small language. The two leading tools for getting an AST are Esprima and Acorn. Acorn can edge out Esprima in parse speed in certain circumstances. They're both built for speed. But it's important to note that they both produce the exact same format of output. They both produce Parser API formatted nodes, which is a format that's well documented on the Mozilla Developer Network wiki. Also, thanks for the Mozilla Developer Network. Another tool that makes generating and manipulating ASTs easier is called Falafel. It takes a string of JavaScript input and calls a function for every node that it visits in depth first order. That function has the chance to replace that node's structure. It runs Esprima under the hood, and it's one of Substack's projects. It supersedes a prior library called Burrito, so there's definitely a food theme there. As a bit of a tangential note, many of you are probably already aware of this, but it bears mentioning. From within JavaScript, you can get the original source of a function by coercing it to a string, by adding a string to the function or calling toString on the function itself. You can then use the function constructor or other safer means like iframe sandboxing to reconstitute a function from a string. There's a really awesome property of JavaScript, and it lets us dynamically change running code, if you're into that. So that's kind of how you go about it. Create a function, add a string to the function, use the function constructor, return plus that string of a function, and call that, and then you have a clone of that function. I personally believe that JavaScript programmers are, amongst their other admirable traits, uniquely prepared to grapple with the challenge of working with ASTs for a couple of reasons. First, there's a tree structure that very nearly every JavaScript developer has at least a more than passing familiarity with. The DOM. The DOM is a big part of why I think JavaScript developers will experience a more gradual learning curve when approaching ASTs. The DOM is many things. It is a tree, it is nested, there are nodes, they have siblings, they have parents, they have types, and it is complicated. You may or may not remember how bad DOM programming used to be. I won't delve too far into it, but suffice to say, it was bad enough that JavaScript tried to ease the pain by adding the with statement. So, yeah, pretty bad. Further, the DOM, like the bytes of our JavaScript function versus the AST it represents, has a textual counterpart in HTML. HTML creates the DOM, and the DOM can produce or accept new HTML to produce new DOM structures. JavaScript as a language and as a community tried many approaches to this problem of working with such a complicated structure. Eventually, one style clicked. Query this tree structure using CSS selectors and consume what you output. I'm talking, of course, about how jQuery changed the JavaScript world. Select using CSS selectors, consume HTML to produce DOM objects. Regardless about how you feel about jQuery, the library itself, the concept is very solid and is now baked into the DOM with query selector all. CSS works very nicely because it has some great properties for our purposes. Selectors are really easy to transform into a matching function, a function that takes a node and given that node and its parents and previous siblings, can determine whether or not the node matches. That is to say, you can't select ahead of the current node in any sense. You couldn't write a CSS selector that says, give me all paragraphs who are succeeded by divs. You could write the inverse, though. Give me all divs preceded by paragraphs. This happens to match the information available to us when we traverse the AST depth first. Selectors are also very terse and can encode a lot of the common relations very easily. In this case, relations between nodes can be codified into one of 4 operations: direct siblings, direct parents, and indirect parents. So that's the indirect sibling. So any p that is a previous sibling of a div at any distance. A direct sibling has to be directly next to the div. Ancestor of the div, the direct ancestor. Or an indirect ancestor, any div that is inside a p at any distance. It's best to read these selectors from right to left. That's how they're executed. The first test passed, then we traverse to the next test, all the way to the left of the selector. So we go from the div to the p, and those operators in between tell us how to get there and when we can't match. They also have the ability to represent and check a given node's type and its attributes, and also the ability via pseudo-classes to check other positional information about the nodes: first child, nth child, etc., whether or not the actual node is empty. Commas also represent alternatives. If any selector in a group of comma-delimited selectors match, the entire selector group matches. And finally, CSS4 brings us a lot of useful features. The any or matches pseudo class lets us borrow the comma behavior for individual nodes. So you can actually have a traversal up to anything that is a block quote or a div. And my personal favorite, the subject selector, which is really handy for our purposes in ASTs. This lets us change the subject of a selector or add multiple subjects to a single selector. So in CSS parlance, what would happen if we added a set of rules to this is that we would style the parent div, not the p itself. By not providing a subject selector, it's always the rightmost node selected, or rightmost part of the selector that is your subject. But with this, you can actually change the subject of your selector and manipulate or return multiple nodes. So I wrote a module called CSS Sauron that aims to make it easy to leverage these nice properties against any arbitrary tree structure. So for example, because for those of you that know me, I have to include a Gary Busey reference in pretty much every code example, so here it is. Basically, CSS Sauron says, tell me how to traverse your particular flavor of tree. What's a tag look like? What's a parent look like? What do IDs or attributes look like? And I'll give you back a compilation function that you can pass selectors to, and I will give you back a matching function. So you can have your wonderful tree of Buseys selected for only Buseys that are the descendant of Gary, not Jake Busey of Starship Troopers fame. And you can tell whether or not a given Busey node matches. There are pre-baked modules for GLSL, JSON, XML, and HTML, and of course, JavaScript. So that's fun. So for example, applying this to JavaScript, what does this look like? The node types become tag selectors, lowercase and abbreviated, because the actual MDM parser API is a little verbose, and it's nice to shorten that up a bit. Their relation to their parent node becomes their CSS class. Going back to the if statement example, ifs have a child node called test. To write a selector that only passes for nodes that are the test relation to an if node, we could write the above selector. And we would select if x greater than y and the y greater than z nodes. So there's tools around this too. And there's other people have tools as well. Grasp is a recent one that came out that's pretty awesome. These are the ones that I'm most familiar with. Rewrite.js lets you transform JS using these selectors. JIC is a backronym for JavaScript Inspection Knife, because it's hard to come up with an acronym that fits, but it's easy to type on the keyboard. And it lets you search your directories and all of your JavaScript using these selectors, and then perform a specific action as a separate step. Scoped and escoped will tell you from your JavaScript what the scope structure is, and that's kind of fun and useful. And JSL is, like ESHint, a AST-based linter. And you use that by defining CSS selectors. So this is demo 2. Well, it would be demo 2 if I could find my terminals. And as far as presentation software goes, it turns out GNU Screen, not bad. Okay. Get everybody on the same page here. Sorry for the delay. Okay. So the first demo is finding XSS in your site. You might be aware, by inserting HTML chunks that you assemble yourself into the DOM, you can, through JavaScript on the front end, cause no lack of grief. So we'll take a look at this example. And if it's hard to see, I can invert as well in crazy minus worlds terminal mode. So this one's just grabbing the body. It's getting JSON from some endpoint. And instead of actually creating nodes in the same way, we're just assembling HTML together and dumping it into the DOM. And this is especially worrisome when you're coming into an existing code base. And there might have been this code. And it's hard to find necessarily. So one thing you can do is something like this. So I'm going to use, again, the magic of Vim. And that's the output of that command. So in example.js, we found all the nodes that have HTML that are the child of a binary addition. So any place we're concatenating HTML together. With the subject selector, as you can see, we don't get a lot of information there. There's not a lot of context. We're just getting the actual strings. But with the subject selector, this guy, we can get more information. We can select up the tree and say, OK, I want to see the actual binary operation itself, which is super handy. You can also search your entire code base with the ****, the globbing syntax. And we can find them in things like Lightbox if we wanted to. This has proven handy in the past for me. Another use. So before modules existed, there was a tendency to staple your methods, your custom methods, onto other objects, say jQuery plugins. And once introduced, it can be kind of hard to find those and remove those and move those to a more modular format. So here we have some code actually pulled from Read the Docs source code, which is an awesome project. And I'm not in no way shaming them here. They're doing great work. But say we want to find every time all the methods, every method that's used in the entire thing. And you can see all the methods that we use really easily. And then we can specify using the attribute selector. So we're going from every call that has a lookup underneath it, the direct child of that lookup. So a lookup is like x.y, say. And we're saying x.y. And then what that really looks like is x, y, like that. And we're saying, OK, the first child will be this x, and the next thing will be this y. And this y, we want to say only if it is on. So anytime we're binding an event handler. So any event handler we find in our code, we want to run this function on. and dutifully it does that. We can also use the any selector to find more than one thing. So focus, click, since jQuery has porcelain functions for those, we can find all of them. And then we can also select up as well. So this actually shows how you can take a different action on the output. So we have the selector here as the first line, same selector as before. And then in sort of a awk sort of way, we have some JavaScript that we can run on each of those nodes. So in this case, instead of printing out the node's contents, I'm just printing out the range of bytes in the string. Again, handy. You can perform all sorts of wonderful little manipulations like that. So the style guide. So let's show the code first. Some folk have a pet peeve that you should always return early, and then not have an alternate. So if you can say if x, return x, you don't need to have the else, because it'll never get hit if you enter the if x. We can actually write a style guide thing that's executable that's really easy to run this. We can say if we use the program JSL, which is there to give us a really easy way to create a CLI linter. And we say any if node with an alternate that has a consequent, and the consequent has continue, break, or return in it, we should be returning early. And that's just how you specify the rules. You give it a selector, and you give it an action, and you give it an error level, so error or warning. Your function gets the node, something to turn it into source minus comments, and then an alert function that takes the node and the warning message. And in this case, if we are the main module right now, we run the CLI. So it's really easy to write your own CLI with this. And we just ensure that it actually does work. So our newly formed linter is a little bit more democratic. It's easy to write new rules for it. The next thing is what rewrite.js was for. So say you make a new rule, but you want to enforce that rule across your code base. Or in this particular example, say we have changed our minds about a test framework, say tape, and we want to move to Mocha for the sake of argument. So we have our So we have our original version of the test suite, which looks like tape. It's not in any way a pejorative against it. It's just the name of what it is. And we can easily either write our two Mocha commands as a series of selectors with actions to perform on it. So this basically maps to falafel running against each of these things. Pretty much what we're doing is we're rewriting the require of tape to the require of assert, because we need an assert library. You can use chai if you want. We're saying that we know end. We're going to take all of our end, test.end things from tape and transform them into done, like Mocha's form of asynchronously done test. And we're going to say tape says equal should be strict equal. And we're going to move that back to strict equal. And then other than that, we're just going to wrap it in a suite. So the nice thing about this is that it takes your program on standard in, and then as an argument, the transformation module, and then it outputs the result on standard out. So you can do things like highlight, rewrite.js, to Mocha, and actually have it rewrite in place. In Vim, say. If you just want to do it from the command line, you can do that to Mocha, and I'll output it on standard out. So you don't have to be married to the technical decisions you've made, which is nice. Okay, so probably best to go back to normal view. Okay. Okay, there we go. Normal view, sweet. So what's next? Remember that AST represents just one additional facet of what our textual code represents. There are other relations that are there between the nodes. For example, there's scope relations. So knowing when one identifier, like which set of these identifier nodes are all the same and where you can change that. Or given a single AST node, give me the relation of all AST nodes that it depends on. So this x plus y depends on a prior statement setting x and setting y. And then within that, we kind of nest down. Any given node can be thought of as a function of all the operations that led to it. This enables automated refactoring or conditional test running, which is pretty cool because then we only run the tests that we know had dependencies on the code we changed. Or if we want to change the signature of a function across an entire code base really easily. There's room for improvement there. We can democratize style guides this way. Anyone can add a new rule with the transformation to apply it to everything. And we can leverage other great JavaScript projects to make these tools even more powerful. For example, you could get into the LevelDB community and use LevelGraph, which is actually a graph database on top of LevelDB, and store your AST nodes there, and their dependencies and their relations between each other, and query from that. Or, even further, leverage the work that's been done with JS-Git and store those as changes over time. We can abstract CSSORON and have implementations for other languages that might be running on the back end at the moment. So all these languages have an if statement. All these languages have expressions and just normal statements. We can make an abstraction over the top of these and query across your entire code base for patterns. And that would be super cool. Ultimately, building tools like this can reduce the cost of our technical decisions. And the easier we can change our minds, the more often we'll make good decisions, just by volume. And interestingly, it points to the idea that as developers, when we look at that text of our code, that level of abstraction, and we're actually operating on another level of abstraction higher. We're operating at a symbolic level. We're able to make these connections like swap out test frameworks because we know that they are symbolically equal without the code being exactly the same. So, in summary, by using one level of abstraction to affect another, you get superpowers. We can make changes that we could not make safely at a merely textual level. And as a JS developer, you are in a great position to build these tools to give others superpowers. You are familiar with the DOM, and you are familiar with all the modules that are out there. You can make programming better for everyone this way. And also, thanks.